So there are three major results from the mean value theorem. But before we state some of these results, you need to know the formal definition of what it means for a function to be increasing, particularly a continuous function. So let f be continuous and defined on an open interval I if there's some x value x sub 2 such that f of x sub 2 is greater than f of x sub 1. When x2 is greater than x sub 1, we say f is increasing on this open interval I. And then you may denote this by these two symbols. Similarly, if f of x sub 2 is less than f of x sub 1, when x2 is greater than x sub 1, we say f is decreasing on this open interval I. You may denote this decreasing action by these two symbols. Now, your classic example of inverse tangent is an increasing function on an open interval from negative infinity to infinity. So your open interval here can involve the entire number line. Now, generally speaking, if you're looking at the definition of increasing, here's a picture that could help you understand this a little bit more. I'll leave it up to you to draw a similar picture to resemble a function decreasing. Now, let's continue with the three major results from the mean value theorem. The first one is fairly obvious and extremely believable, right? So if the first derivative is equal to 0 for every single x in the open interval AB, then f of x must be a constant function on that AB. You could draw a picture to help you remember this. Now the constant function will look something like this. There will be a hole, and the output value will be straight across. The second major result is a corollary of the previous theorem. If you haven't heard of the word corollary, all this means is that this is a baby of the previous theorem. Literally, it's a direct consequence of what's stated up here. This corollary says if the derivative of a function is equal to another derivative of another function for every x in the open interval AB, then the difference between those two functions is a constant on the open interval AB. And if you look at it that way, if you just said f minus g, if f of x minus g of x is just some constant c, if you add g of x to both sides of this equation, you realize that the two functions only differ by a constant. This is extremely important in the study of antiderivatives. So the mean value theorem is extremely important in the study of integral calculus. Now, another major result goes back to that idea of increasing or decreasing. So here is the third result. It's also known as the first derivative test. Suppose a function is continuous on a closed interval AB and differentiable on an open interval AB. If the derivative evaluated for all those x's on that open interval, then f is increasing on that open interval. If the derivative evaluated at all those x's are less than 0 on an open interval AB, then f is decreasing on that open interval AB. So you could write this in symbols if you wanted to help save yourself some time. And the proof for part 3i is below. It's right there. And being able to read and analyze and rewrite proofs could help you understand these theorems in calculus so much better. Suppose a function is continuous on a closed interval and differentiable on an open interval, and the first derivative evaluated for all those x's are greater than 0. Let x1 and x2 be any two distinct numbers in that open interval, with x1 being less than x2. By the mean value theorem, we can look at this smaller interval, okay? You can look at the smaller interval, meaning this interval here. And we can certainly apply the mean value theorem on this smaller interval. You end up getting a critical number. The difference between the y value is now equal to the derivative evaluated at this critical number times that change in x value. But what do you know about x2 minus x1? You know this is positive because you know x2 is already bigger than x1. So this is positive. We know that the derivative is already positive. So this has to be the product of two positive numbers, okay? Now, f of x2 minus f of x1 is the product of two positive numbers. There is a positive number, and there is a positive number. Stating that inequality, and then if you state this first inequality, we could obviously state the second inequality, and that is the definition of a function increasing on an interval AB. I'll leave it up to you to try to prove 3i, or 3II. The first derivative test will be extended to procedures to help find local extrema, min or max, and in some cases it will help you find absolute min or absolute max. Let's go back to the police and the speed trap. Remember that the state patrol officer saw a car from rest at a highway on-ramp. The officer video recorded the car, probably got the license plate and everything, and radio ahead to another patrol officer 30 miles along the highway. When the car reached the location of the second officer 19 minutes later, woo, that was rather fast. The car was clocked going 65 miles per hour. The driver of the car was given a ticket for exceeding the 70 mile per hour speed limit. Why can the officer conclude that the driver exceeded the speed limit? And the solution, in this case, requires some thinking along the lines of calculus. The car that was traveling didn't travel in a time machine. It didn't disappear. So the car that traveled along the highway had to travel continuously. Not only continuously, it had to travel rather smoothly. All right, we cannot assume that it crashed on the shoulder and then from the shoulder, from a crash site on the shoulder, got back on the highway. Okay, so that means we have to say the function or that car was traveling continuously and also in a differentiable fashion. So let f of t be a displacement in miles of that car over a period of time. And this time t is measured in hours. This displacement is continuous and differentiable on this time interval measured in hours. And note that f of 0 is equal to 0 miles because that's what the first officer said and stated and recorded. And by the time the car reached the second officer, 19 minutes later, we get this output from the function. So even though we don't know the function, we don't know exactly what it looks like, we do know that the car traveled continuously and in a differentiable manner. So by the mean value theorem, there exists a crucial moment or critical moment in this time interval such that the derivative evaluated at this crucial moment gets you this average value, or mean value, or nice value. Thus, the derivative evaluated at this crucial moment simplified to 94 7/10 miles per hour. Ooh, that's rather fast. Thus, there was a time in the first 19 minutes that the driver was driving about 94 7/10 miles per hour. Hence, the driver exceeded the 70 mile per hour speed limit and deserves the speeding ticket.